Hello, everyone, and by everyone, I mean the two of you. Um, Welcome to Module 6. I went ahead and kind of departed from the typical pattern of talking about the modules on Thursdays and details on it on Monday to go ahead and wrap up Modules 5 and 6, primarily so that I'm not blocking you if you're moving through this rather rapidly. So I think you'll find some of these are pretty quick compared to some of the other ones we've done. So today we're talking about statistical model validation. So the basic idea here is, how do you know if what you've built is good, right? A very fundamental question and very relevant, right? Because you need to be able to both assess it yourself and also defend your model later on. So a very pertinent topic and very relevant to anyone's professional experience. So not surprisingly, the core competency that you're dealing with in this module is around validation of statistical models, or models in general, frankly. If they need not necessarily be statistically based, it could very well be connectionist based, right? So you could be evaluating a neural network model to see how well it's doing as well. You also need to be able to handle the concept of a holdout sample. Basic idea there, pretty simple, and you've been doing it. You probably did it in numerous courses before this, but we'll talk about it formally from the perspective of separating your test from your training set, and then the variations that you can do with cross-validation to be able to handle the case of maybe not so much data. And then also, how can the holdout sample approach being used as a validation? It's the whole basic point of it, right, is to ensure that the model is tested on something it hasn't seen before that you know. So a labeled data set that it has not seen during the training. There's also another set, and we'll talk about those in a minute. Actually, we'll talk about it right now, a validation set. So this is a common pattern. I'm reusing this slide from a classification course that I also teach, but it's the same thing. This is what we do as data scientists, and it's what we do as artificial intelligence people as well if we're doing AI work. There are basically three sets of data. The training set, you know what that is. That's what the model sees during the training process, especially whenever you're dealing with what this is, which is supervised learning. You're telling it, here is some stuff, and here is the thing that goes with it. Here's the answer. And it adjusts itself in some fashion, be it through some sort of statistical weights. Maybe it's connectionist approaches, where it's the factors inside of the deep neural networks, or the neural networks. But regardless, you're basically showing it data and telling it, here are the features, and here's what goes with it, the target. And then two other ones that you may use, depending upon what type of work you're doing, is a validation set and a test set. Test set we'll go ahead and talk about because you've seen it as well. It is used to assess the overall performance of the model at the very end. So you take your test set, your data set that is originally given to you, that is labeled, you separate it by some fraction, generally something like 20/80, where 80% is for training and 20% is for test, maybe even 25/75. There are extreme cases where it might even be a very small percentage of the test set if the number of records that are relevant or are present are maybe not all that varied, and you think you can get by with a smaller test set percentage-wise. Then the last set is a validation set, and it's used whenever you're wanting to figure out what works better. So you still set aside your test set. You don't ever see it until you're done, right? That's the key concept. You don't use it during that process, but you use this validation set to tune hyperparameters. Hyperparameters, fancy word for settings on the model. So perhaps if it's k nearest neighbors, what is k? What's a good k, right? So is a very simple example. So that's the basic concept. And then when you do all this stuff, you generally want to go back and compare the metrics that are associated with either different algorithms you're using or different hyperparameters, right? So you need a way of knowing what good looks like. What is the metric that is your concern? Could be accuracy, probably is accuracy, but it might be something else, like maybe you're wanting to really avoid a false positive or a false negative because the consequences might be disproportionate for one of those. So you may be more complicated than just a simple accuracy or F1, but it's something that has to be done, and it's essentially your metric. It is the thing that you use whenever you're determining what is good and what is not good. That's where things like AutoML come to play. You basically give it a data set and the metric of determining what is good, and it goes through literally thousands of algorithms and variations on hyperparameters, and then returns back to you, well, this is the model you should use based upon the metric that you've given. There's other factors that will go into your determination of what's a good model. Could be things like how long it takes to run and reach potentially convergence, how well it handles data it has not seen before, and so on. So those are all kind of elements that we consider. Also, whenever you're talking about a model and assessing it and being able to decide if it's good or not, is some things like transparency. Can you explain why it's doing what it's doing? And can you interpret the results of the model in a pretty straightforward way? Is it consistent, right? Does it always return something similar? And also moving up this pyramid, when you go up into the accountability, does it accurately preserving privacy? Is it robust? Is it reliable? Is it safe in the sense that if a false negative or a false positive is something really dangerous, like say maybe on some sort of diagnostic test, then that might be really important. And then the last one is around being fair, right? Is the model fair? That's less of a concern whenever you're dealing with statistical things, unless what you're doing involves some things that are naturally going to introduce bias, right? So make sure your data set is both fair and equitable and so on, a reasonable representation of the population that it will be seeing, but also make sure that you're not including any factors into the model that are unnecessary that could result in inequality. This is something that's pretty important. So you want to make sure that you've got a diverse data set, you've got an inclusive set of things going on as well. Where this becomes really important is if you've got minorities or gender biases that are occurring. If you've got a bias in your data, you may have a bias in your trained model. A good example of this is in speech recognition. There's oftentimes a bias towards someone speaking with a certain way that perhaps is like a white male, as an example. Or if it's being trained on speech by people in India, perhaps even if it's intended for English, it might be biased in a way towards Indians' accent of English. And also making sure that there's a representative distribution inside of your sampling of gender, right? So you wouldn't want it to be such that a voice recognition algorithm does really well on men and does horrible on women because you just didn't train it correctly. And so those are all things to take into consideration whenever you're assessing a model as well. The general steps that we go through, you've done this before. It's basically you load the data, you take a look at the data, you do some exploration of it, figuring out what's the characteristics of the data, maybe what is the variance of the various features. Somewhere through there, you're probably going to do some feature evaluation to determine what are the important features, what moves the needle on the outcome and so on, what's the variance of the various features and so on. Then you do this split to where you split your data into the train and test set. Then you do typically standardization, so you'll bring things into a standardized scale and possibly doing some transformations along the way. Then you'll create essentially a classifier or some model, and then do a test essentially on it to see fitness. Most of the time we are doing prediction, that's and classification. That's kind of, if you'll notice, what we've done a lot of in this course. And it's the next step is to take your model that you've trained and use it to do some predictions, and you test it against your test set to see how well it did those predictions. And that's the basic steps that we go through. To restate it again, split your data into a test set and a training set. You never, ever, ever train on your test set. That's one of the key things, with a possible exception, and we'll talk about that in a minute. And after training, you test the model using your test set to do your evaluation. The easy way to do that is with the scikit-learn test train, or train test split macro that makes it really just drop dead easy. Cross-validation is kind of what I alluded to where you kind of are training on it, but not really, not in a given iteration. So the basic idea is that you do iterations inside of your cross-validation. In this case, we're doing 4 iterations. That basically means that 4 different sets of data were created, and on each one of our iterations, we use a different one for our test set versus our training set, the other three. So we hold one out on each time, and so we go through and we say, okay, it's the first time through, it's the first one, then the second iteration on the cross-validation is the second, and so on. So it's a way of basically, with a limited amount of data, potentially doing a reasonable estimation of how well things are going. And so with that, I'll stop showing you slides, and we'll actually start doing some stuff. So switching over, starting at the first, we'll do the code that that's interesting, that was supplied with the course materials this time. It's very much a kind of the manual way of doing this, and as I mentioned, it's kind of is a little slow. So what we're going to do here is some random forest classification, just for to basically pandas will show me all the columns, and then we can load the file. So we're using the same biz rate or bizloans ras file, and so the first step here is to essentially create a split based upon a 25% train, 25% or 75% train, 25% test sort of distribution. So there'll be 3 times as many records used for training as there will be for testing. And then there's a lot of discussion here around random number generation seed setting. The primary reason that you'll see people setting a seed in a random number generator is for repeatability. The random number generator is actually the proper name is a pseudo-random number generator. What it does is essentially has a mathematical formula that's utilized to produce numbers, but it has to start with something. If you don't supply a seed, it typically uses either your clock time or your tick count off of your processor as the seed, so that it's somewhat random. It's random at that moment in time. So if you run it normally twice, you'll get different values. They're doing this in order to create a uniform distribution across the data frame, essentially setting if something belongs in the training set or not. That's how this is being done. So it's using a distribution, setting an attribute on side of it, on it, and then selecting, filtering, essentially doing the splitting the data frames based upon that value after it's been set. So we can go through and load the file and create that new column, so we can take a look at it and see that the thing we created is indeed out here. And the first few happen to say is train. Let's see if we happen to get lucky on the tail. I'm not sure what that was. And yes, we did. We got some falses on here. So most of this is train, as you would expect. So if you look at 10 records, we should see about 2.5 of them, and that happens to be pretty much what we're seeing. So we also, if we were to do this, assuming it is a truly uniform distribution, there should be a couple of them in here. And that's one of the oddities of random number generators, is that while it may be uniform across the entire thing, each one of them is truly random. So here we've got a few more falses, so at the end of the file. So the next step is to actually do this. This is doing the split. We're creating our test set and our train set by simply saying the first one comes back is if it's true, the other one comes back if it's false. So we run that, and we can take a look at now the head, and these will all be, or these are all the training set, and these are all the test set. And if we want to go real crazy here, we could potentially do some checking to make sure that and this is where I'll have to remember. So there's test has 1479, and that has 43. So about 4 times or 3 times as many. So yes, it does appear that it did a reasonable sort of split. And then the next step here is to go through. We've got them split into 2 different data frames. Then we want to basically create our targets and our features for the actual training. So we generally call those X and Y. y being essentially the target we're looking for, x being everything else but that thing we're looking for. So we create those, and then now we can do our training. So we're running it through and doing the fit on the random forest. Now we can go through and essentially test it on the training set that we sent through. So it's one sense to determine how well things are doing whenever you run it through and determine how much error exists whenever you're doing it on just the training. And with this sort of particular algorithm, it's zero. It nails it because it created a random forest that hits it pretty well. There are other situations where even whenever you train it and you run it the test set again through, or the training set through it again, there will be differences, and especially when you're dealing with things like connectionist approaches. And in fact, that might be good because especially when you start talking about neural networks, you have the potential of overtraining, which basically means you're fitting the training set too well. So if you were to get zero error on the training set, that may mean that you've overtrained, right? So you always have to keep those things into consideration. Now, if we run this against the test set with the random number as being 1, we get back that it's around 90% accurate, give or take, so 10% error. So that's not too terribly bad, right? The 90% is pretty good, and some of those are a little bit over 90. So not a bad sort of approach. Now, that's kind of the hard way, right, to do all that. So the easy way, or easier, right? And you guys, this is nothing new. I'm sure you've seen this tons of time. If you haven't, well, you can thank me later. So the same basic thing. We're just loading up the file. We're creating our X and Y, and this is a little different because I'm creating my X and Y data frames before I do the split, right? So I'm separating X and Y, and then test train split. You give it X and Y. Tell it what you want the test size to be. You give it a random state if you're so inclined, so that you get repeatability. If you want it to be truly random, you leave that off, right? And then basically we've created our sets. Then the next thing is to simply just train on the training set. Then do some prediction against the test set, so get those back, and then score it and see how well we did. And guess what? It's right around 90% accurate. So if you really wanted to be and go to this, so we run it again, and then to see the error, it's just 1 minus, right? So times 100 and wonder why that went negative. Oh, because I didn't do my math right. Times 10 then. Anyway, so get the basic idea that it is. Pretty sure why that's doing that. Oh yeah, that's right. So that's right around a 9.1% error, right? So in line with what we were seeing on the other. And then if you want to go to the next step, you go ahead and do the confusion matrix to see how well you did on that particular prediction of where you got it wrong. So that's pretty much the holdout, right? Pretty straightforward. We've been doing this, I'm sure, numerous times. I doubt what I'm presenting is new, and hopefully it's been covered numerous times. So now the one that is kind of a little more to drill into, cross-validation, because I had to clear a few cobwebs here as well. So the basic idea is sometimes you don't have enough data, right? And to combat that, you have the ability to do some form of cross-validation. A common form of cross-validation is the k-fold cross-validation. And that's what we talked about just a little bit ago, where basically you have some data, but it's not quite enough data for you just to set aside 25% or 20% of your data for the testing. So what you do is you partition your data into slices or chunks of data. In this case, we're taking a string from A to J, and we're basically partitioning it into 5 different groups made up of two things, right? And so then the basic idea is you've got these slices of your data, and then you iterate through those sets so that on the first pass through, so your first cross-validation iteration, you'll have one of them you hold out, which is in this case group 1, so B and I get held out, and you train on everything else. Then on the second iteration, you switch to the second group and hold it out and train on everything else, and then you use that test group for your actual validation. So it's a way of you're not using your test set at the same time as your training set, but portions of it are being considered along the way. Obviously, probably it's better if you've got the data not to do this, most likely. Maybe, but it is a way of combating limited amounts of data. So let me clean this up just a little, and then we can go take a look at it. If you're so inclined, the Scikit Learn pages are really pretty good, especially the user's guide. It goes into a lot of detail about it, including a pretty good discussion, and this is where I stole the image from, of how k-fold works, right? And so we'll see that in a moment. But so it's widely used, especially whenever you don't have a whole ton of data, right? So typical imports, pulling in our random forest classifier and so on that we've done in the past, and as well I'm going to start off with their example, which is a lasso approach, right? So pretty straightforward. You basically create your model, and then you supply your model as a parameter to the cross-validate, and you give it the X and Y, so your features and your target data set, and then you tell it how many iterations you want it to do, so how many different cross-validations. And then you essentially can produce the result of for each one of those, what did the test score turn out to be. Some of them, in this case, are really pretty good, and others are really not so good, right? So kind of an interesting sort of thing to consider. So breaking down what these parameters are, the estimator is essentially the model, right? That is what you're using to do the fit. So that's literally what it's going to do. It's going to call fit on it, right? X is the data to fit. Y is the target variables that you're going for. And C is the cross-validation number of iterations that you want to do. If you're doing k-fold, right? So if you give it an int, that's what you're doing. If you don't give it anything, it's going to default to 5 k-fold. So k will be 5, and the same thing as passing in 5. So that's the default. And then a few other things, but as a general rule, you're probably going to be doing k-fold. That's kind of the normal sort of pattern. And that's kind of it. So this is a visual representation of what I've just said, and it's the same slide we saw, or same image we saw earlier. So the basic idea here is that you are taking a portion of your data, holding it out on each one of the iterations, not the same one. You never test on what you're training, or you never train on what you're testing with for a given iteration, but it does vary across each one of those iterations. So a representation of that is here. So we've got a set of values, A, B, C, D. We're going to split it into 2 different things. So the first time through, 2 and 3, and 0 and 1, and then the second time 1 is 0, 1, and 2 and 3. So we're basically, for the first time, we train on one set of it and we test on the other. The next iteration, we do the opposite, train on the other one and test on the other one. So back to a quick example of using the random forest classifier against using it with a cross validate of 5. So we're doing 5 iterations, and we're doing that, and it takes a little while because it's actually having to run through that with those. Probably not a great use with this much data, and we can get back a pretty odd range, right? In certain sets, it does very poorly, and others does pretty well. So kind of an interesting thing versus just training on it. So that's cross validation. And to switch over and talk about R, the similar sort of holdout approach. So we start off, load the file into the data frame, setting a seed of 1, and doing the same sort of basic approach, right? So we're going through and deciding which one of them is trained, splitting those into 2 different data frames, test and train, then doing some fitting here. So we're going to do some model fitting, and then eventually it'll finish. And then we can take a look at the data and calculate the accuracy, right? So that's pretty much the same sort of approach, and I'm sure there is a much simpler way to do that in R as well. So with that, we've ran through at least 2 of them. I'll skip over SAS. I don't think anyone has really embraced it for the assignments. So talking now about deliverable 6, which is validating models with holdout samples, competency validated statistical model. So you're still the data scientist working in Frostbite Falls Bank. Your bank has collected a large quantity of data regarding loans at the time of origination and whether or not the loan was repaid or defaulted. In a future project, your bank intends to develop a predictive model to assess risk. However, there is a concern of some of the models might overfit. So you may do really well on your training set, but you may not do as well on unseen data. Your manager, Paul Fries, has asked you to develop 1 or more models to predict loan default. Your manager wants you to randomly split the data into 2 data sets, a training data set and a test data set. The training data set will consist of approximately 75% of the data, and the test data set will consist of 25% of the data. Your manager wants you to develop a default model using the training data. Then the model will be used to predict the results for the training data set if the accuracy is similar for both data sets. Then the bank will be comfortable using the model. So kind of interesting. Follow the steps below to develop a regression model. So you're doing regression to predict the probability of default. Select 1 or more of the following programming languages, SAS, Python, R. Mastery is achieved by demonstrating 2 of those languages, or if you want to go crazy, you could do all 3. For each programming language, do the following. Take the data set and randomly split it into 2 data sets, training and test. Then the training data set will consist of approximately 75%, test 25%. For each sample, you will create a probability of default model that incorporates variable selection. You may use logistic regression, trees, or random forest to predict default. Make a note of the error rate for both the training and test data sets. Discuss whether the error rate from the training and test sets are similar. Interpret these results and make a recommendation whether the model or models could safely be used by the bank. Assess whether the chosen language or modeling approach may or had any effect on accuracy. So what you turn in, a text file with each one of the programs, a Word document that contains screenshots, including some sort of combining them together into a single Word document is what makes a ton of sense to me. And then write a memo that basically says, how did you split it, into what sort of distribution, or percentages, how was the model developed, the accuracy of the training and test sets, and comment on any noticeable differences in accuracy when the model type or language is altered. If there are no noticeable differences in accuracy, make sure to state this fact explicitly in your memo. We're familiar with the data set. You guys are all going to go for the mastery column. That's where you've been playing all term anyway. So the source code multiple programming language is accurate and well written. You guys write great code, so no worries there. You do provide some screenshots, clear and well planned. That shows a full understanding of accurate outputs, clear and thorough description of the method used to split the data, the models developed, and accuracy of training and test data sets, and then a clear and thorough commentary on noticeable differences in accuracy when the model type or language is altered, and then a clear and thorough commentary on noticeable differences in accuracy when the model type or language is altered. So either I copied the same thing twice or there is a mistake in the rubric, so do double check me. I'm presenting this for convenience. Don't assume that I got it totally right. So one last thing I wanted to do, I know we're running at a little bit over half an hour, but this is kind of cool. So I may revisit this for a subsequent exploration. So this is orange. You guys have probably seen this as well. I'm loading up the BizLoan data. It knows that the target is bad or loans, and then we've got some numeric features, right, and then some categorical stuff. So it's doing a reasonable job loading it up. So I'm going to use test and score. Really cool thing, right? So if you're not familiar with it, we can basically say I want a random sample, and let's say we want it to be, the training set is 75%, right? So then once you do that, the last thing is you're probably going to want a confusion matrix. Then you can hook up various classifiers. So I just hooked up a random forest. It's setting up with a number of trees is 10, and do not split smaller than 5. So those are the defaults. And when I did all that, it calculated basically the accuracy, right, and the AUC and various other things. So pretty cool stuff. Also, because I hooked up this confusion matrix, I can see where it's missing. So pretty accurate on 0, 0. Not so good down here, but whenever the actual is 1. So when it's actually bad, then it doesn't do so good, which is the one you probably really want to know, right? If it's bad and you predict it to be good, 34% is kind of a problem. So where it gets more interesting, let's see, what was the other choice? Logistic regression, I think they said that was an option. And so we can see logistic regression, not real good, right? Actually worse. And you can switch over to the logistic regression, and it's not doing very good at all on saying something that is, it basically just seems like it's saying everything is good. That's what it's doing. It's biased towards that. So additional ones, naive Bayes, and throw in a neural network, and Ada Boost. It usually does pretty good. So a little bit of bagging going on there. And maybe the rule. And it's going through now and calculating and scoring those various ones. Some of these haven't quite finished yet. It takes a while whenever you're doing neural networks and so on. I don't think that it's using my GPU. There's probably a way to turn that on, but probably it's some sort of additional configuration, because I don't think it's using it. And whenever you start doing things with neural networks, always a good idea to have a GPU turned on. So what we can see is that it has gone through and finished 3 of them. Naive Bayes, random forest is probably the one I would lean towards, although this is a slightly better on the false negatives, right? And it is running through, still working on it. And that's not a good sign. It's going to take quite a while. That's probably this. So if I take that off, drop too many too quick. let it something finish. Okay, so AWS finished. And you can obviously sort these based upon whatever you think is the appropriate sort of thing to consider. F1 being a pretty good one a lot of the time because it kind of balances between. And turns out random forest is doing pretty well. Let's see if rules, and what is my rules set to? It's not too bad, but it's going to take a while. So anyway, if you haven't played with it, go take a look at Orange. It's a quick way of doing some kind of quick exploration. Data mining, I think is what it's called. Yeah, Orange data mining. Free and very cool university-based sort of tool that came up with it, barely touching the surface of what all you can do in it. So do feel free to go out there and take a look. I guess as a brief sort of thing I can show you, you get a data table where you can take a quick look at your data. It's kind of busy right now, so that's going to take a bit. You can also do data info. It has the ability to do your own sort of proper sampling if you want to. This is doing sampling inside of it using the appropriate sort of random samples. And it looks like it's repeating multiple times with random samplings, and it is doing some stratified sampling as well. So that could be contributing. That repeating bit's probably why we're taking a while to run. But you can actually do something like go take your file in, do a sampler to basically say I want to have 80% going out one path and 20% out another, and then you can draw from here to something. I'll just do a table for now. Do a similar thing down here to a different table. Click on the line, remove it, and say that you want it to be from the remaining. So that's your test set. You can also give it or give things a name, so you could actually rename it if you click on the right thing. You can call this test set, and so on. So very powerful. Not quite what you can do with programming languages like Python or R, but if you want to have a quick sort of go at the data, it is an excellent way to get a sense of what's going on. One of the things I may talk about in the future, if there's an interest, is AutoML. Very cool technology, and we could do a bit of a walkthrough and a demo with this data set in AutoML and figure out how well it does. So with that, I'll wrap this up. Stay safe as always. If you have any questions, do let me know. That's what I'm here for. If something's going on, also let me know that. I'm here to help. If you have any questions about anything, do ping me. And stay safe, and we'll talk again soon.